In 1917, a man named Glenn Curtiss built something he called the autoplane. 3 wings, 4 wheels, a propeller at the back. It looked like someone had attached a biplane to a luxury sedan and genuinely believed that was the future of personal transportation. It hopped briefly off the ground during testing. It never achieved sustained flight. The newspapers called it revolutionary. The revolution never arrived. That was 109 years ago. 109 years of engineers, investors, governments, and dreamers, all pointing at the same horizon and saying the same thing. Flying cars are coming. Personal aviation for ordinary people is almost here. The breakthrough is just around the corner. And for 109 years, the corner kept moving, until now. Because the corner did not move this time. What is around it is not a concept or a prototype or a promising early-stage company burning through venture capital while it negotiates with regulators. What is around it is a certified autonomous flying vehicle carrying paying passengers on commercial routes in Chinese cities right now, today. What is around it is a foldable flying machine that deploys from the back of an electric truck with nearly 5,000 confirmed orders and a factory already built to produce 10,000 units per year. What is around it is a personal flying vehicle on sale for $4,937. And what is around it is an engine for a family car that a Guinness World Records adjudicator certified at 106 miles per gallon on a public road. 109 years of the same promise. And the country that finally kept it is not the one that made it. That is the story we are going to tell today. All of it. The full century of failure that made this possible, the specific things that have actually been built, the obstacles that are genuinely still there, the military and environmental dimensions that the promotional materials skip past, and what happens to the world when the sky becomes as routinely traveled as the road beneath it. This is not a hype video. It is not a countdown of cool vehicles with background music. It is the complete picture of the most significant transformation in transportation since the automobile. And by the time we finish, you will understand exactly why the countries watching this most carefully are neither dismissing it nor celebrating it without reservation. They are taking it seriously. You should too. Hit the like button right now. The research behind this is extensive, and every like helps it reach people who want substance rather than spectacle. Subscribe and turn on notifications. This story is moving faster than the news cycle can keep up with. Let us start at the beginning. The graveyard is worth visiting before we look at what is still standing. Terrafugia, founded 2006 by MIT graduates. Serious engineering, serious money, never sold a single unit to a single customer. Acquired quietly by a Chinese company in 2017. Most of America never noticed. Lilium, German electric aviation startup, raised over $1 billion, filed for bankruptcy in 2024. The annual economic output of a small Pacific island nation, spent, gone, finished, without a single commercial passenger ever climbing aboard. Joby Aviation, still waiting for FAA certification as of today. Archer Aviation, still waiting. Wisk Aero, still waiting. These are not small operations run by naive optimists. They are well-funded, seriously engineered companies doing genuinely difficult work under a genuinely demanding regulatory framework. The waiting is not a sign of failure. It is a sign of how hard the problem actually is when you try to solve it within the rules of the most demanding aviation authority on Earth. And yet the waiting continues while in Guangzhou and Hefei, ordinary people with no aviation background are climbing into autonomous flying pods, tapping a destination on a touchscreen, and arriving somewhere else without having touched a single control. The gap between those two realities is the most important thing to understand about where flying vehicle technology actually stands in 2026. And understanding it requires being honest about something that most coverage of this subject gets fundamentally wrong. The story is not that China is better at engineering than the West. It is not that Western companies are incompetent or Western engineers are outclassed. The story is that China built something that Western flying vehicle development never had. A floor, not the vehicles. The floor underneath the vehicles. The manufacturing supply chains, the regulatory frameworks developed in parallel with the aircraft they were designed to certify. The government commitment treating low-altitude aviation as a national economic priority deserving coordinated infrastructure investment rather than leaving it to individual companies to negotiate their way through existing frameworks designed for a completely different era of aviation. When Lilium was trying to raise its next funding round, China had 30 active electric vertical takeoff and landing companies scaling simultaneously. 30 parallel streams of engineering progress feeding lessons into a shared ecosystem that got smarter and cheaper with every passing quarter. When American companies were in year 3 of FAA certification negotiations, China's Civil Aviation Administration had already written and published the framework under which the EHang EH216S would be certified because they wrote it alongside the aircraft rather than waiting for the aircraft to arrive and then figuring out what rules it needed to satisfy. The West built the blueprint, China built the building, and then opened it for business. Here is what is actually in the building. The EHang EH216S2 is the vehicle that changed the proof of concept into a proof of commercial viability. 16 rotors across 8 folding arms, 2 passenger seats, no controls inside the cabin, no joystick, no instrument panel, no emergency override that a passenger can reach for if something goes wrong at altitude. A touchscreen for destination selection and a ground-based AI control center that manages everything else from takeoff to touchdown. The comparison that makes this feel less alien than it initially sounds is the elevator. When you step into an elevator, you do not control the cables, the motor, or the speed. You press a button and trust the system completely. You do not know who designed the braking system or how many redundancies are built into the motor. You just press the button. The EHang EH216S operates on exactly that principle applied to flight. You select where you are going, and the system takes you there. In October 2023, it became the first electric vertical takeoff and landing aircraft in history to receive full type certification from China's Civil Aviation Administration, not a test permit, a full commercial certification carrying the same legal weight as the certification a commercial airliner earns before it carries a single paying passenger. Government inspectors examined every component, tested under demanding conditions, and officially confirmed it was safe for commercial passenger operation. It then went to work. Tourism flights, short-range transit routes, real passengers, real tickets, real revenue. Over 300 units delivered and operating in the real world, generating actual flight hours and feeding actual engineering improvements back to the development team. The trust question that the flying vehicle industry spent a decade debating theoretically has been answered empirically. Ordinary people willingly get inside autonomous flying pods. They fly, they land, they do it again. The market has spoken in the most direct language available to it. The XPeng land aircraft carrier is the vehicle that made the Western automotive industry look at its product roadmaps and feel something uncomfortable. The problem every flying car company in history eventually broke itself on is the fundamental engineering tension between what makes a vehicle good at flying and what makes a vehicle good at driving. Optimize for one, and you compromise the other. The weight distribution required for stable flight is not the weight distribution that produces efficient ground transportation. The aerodynamic surfaces that generate lift create drag on the road. The structural requirements are different. The power delivery requirements are different. Everything about the physics of the two modes of travel works against designing a single vehicle that does both well. XPeng's answer was to stop trying to solve that problem and instead make it irrelevant. 2 separate vehicles, each optimized entirely for its own environment, engineered to connect seamlessly on demand. A full-size electric ground vehicle with approximately 500 miles of driving range, a flying module with 6 propellers that mounts on top, detaches when flight is required, operates independently in the air, then returns and reattaches when the flight is complete. The transition from flight mode to road ready takes 5 minutes. Publicly demonstrated, on film, repeatedly, under $280,000. Compare that to a light helicopter at $250,000 to $500,000 that requires a licensed pilot, a dedicated landing pad, and between $100 and $300 per flight hour to operate. The land aircraft carrier undercuts the entire value proposition of helicopter ownership while adding road capability and removing the licensing requirement. The factory in Guangzhou is already built with annual capacity for 10,000 units, 10,000 flying vehicles per year from a single facility. The entire Western world has never certified that many electric vertical takeoff and landing vehicles in its complete history of attempting to build them. Nearly 5,000 confirmed pre-orders, real deposits, real names on a waiting list. For context, 5,000 units represents the entire annual global production volume of Lamborghini across every model and every market for a full year. The Autoflight Prosperity set the distance record for electric vertical takeoff and landing aviation. 155 miles on a single charge, Washington, D.C. to New York City without burning a drop of fuel, completed by an autonomous air taxi system with a safety architecture including multiple independent protection layers and AI capable of deploying an emergency parachute in a fraction of a second if a critical system fails. Mid-flight. In February 2026, Autoflight unveiled the Matrix. 5 tons, a wingspan of 66 feet, wider than 3 standard highway lanes placed side by side, 10 passengers, fully electric, the largest electric vertical takeoff and landing aircraft ever constructed, not a render, not a scale model, a physical aircraft that exists in the real world, built in the same calendar year and by the same industrial ecosystem that put a single-seat personal flying vehicle on sale for $4,937. That juxtaposition matters. The cheapest personal flying vehicle and the largest electric passenger aircraft on Earth, both produced by the same country in the same period. That is not a coincidence. It is evidence of an ecosystem operating across the full range of what the technology is capable of, from the accessible entry point to the ambitious frontier. Simultaneously, the $4,937 figure deserves honest treatment because the headline and the reality are not identical, and the difference between them matters. The base price covers the body, the motors, and core electronics. Extended range batteries cost additional. An autopilot system costs additional. Certification for urban flight operation in most jurisdictions requires registration fees, insurance, and in many cases training. The total cost of an operational vehicle is higher than the number that generated the international headlines. But even with all of those additions, the final figure remains several times lower than anything the Western flying vehicle industry has produced. China achieved this through the same mechanism it has applied to every manufactured product category it has entered seriously. Mass production at scale, component costs driven down through volume, ready-made technology adapted from adjacent industries, rather than developed from scratch at full cost. Government support reducing tax burden and subsidizing key development phases. Manufacturing infrastructure that took years to build but now operates at a cost per unit that competitors in less integrated supply chains cannot approach. The $4,937 flying vehicle is not a loss leader designed to buy market share at a loss. It is the natural output of a manufacturing ecosystem that spent 10 years getting costs down to exactly this level. And the trajectory of that cost curve points only in one direction. Now, for the part that the promotional materials consistently skip, the sky is not empty and it is not free. It is one of the most carefully managed spaces on Earth. Every altitude band, every approach corridor around every airport, every airspace classification has rules attached to it that were written for a world where flying was something commercial airlines did with professional pilots under continuous air traffic control supervision. Those rules were not written with a $4,937 personal flying vehicle in mind. Adapting them is not straightforward and it is not fast. The United States Federal Aviation Administration moves carefully and deliberately. That carefulness is not bureaucratic obstruction. It is the product of a regulatory culture shaped by aviation accidents, by the understanding that mistakes in airspace management kill people, and by the genuine complexity of integrating a new category of aircraft into airspace shared with commercial aviation, private aircraft, military operations, and emergency services. American electric vertical takeoff and landing companies like Joby and Archer have been navigating that process since the early 2020s and are still not carrying paying passengers today. They will get there. The timeline reflects reality rather than failure. Europe faces regulatory complexity multiplied across multiple national authorities that must each individually agree before a vehicle can operate commercially across borders. Dense urban development and strict noise standards create additional constraints in the markets where flying vehicle demand would be highest. The infrastructure gap is real in every market. Flying vehicles need somewhere to land, somewhere to charge, and some mechanism for managing the airspace they share with everything else that flies. None of those things exist at anything close to the scale that mass adoption would require. The electric vehicle industry spent years and billions of dollars building charging infrastructure that still has significant gaps in most markets. Flying vehicle infrastructure does not yet exist at meaningful scale anywhere. The city itself presents engineering challenges that open field testing does not reveal. Power lines, communication antennas, high-rise buildings, bridge structures, and the general density of urban infrastructure create obstacle environments that autonomous navigation systems need to handle reliably before vehicles can operate at scale over populated areas. The testing that has been done is impressive. The gap between what has been tested and what mass urban deployment requires is significant. Noise is the obstacle that urban planning discussions most consistently underestimate. Even the quietest electric vertical takeoff and landing vehicles produce substantial sound during the takeoff and landing phases where acoustic energy is greatest. In urban environments where these vehicles would operate most densely, the cumulative effect of high-volume flight operations would be experienced as a persistent and pervasive change to the acoustic environment of entire neighborhoods. This is not a technical problem with a straightforward engineering solution. It is a quality of life issue that will require political consensus and urban planning decisions that go well beyond the vehicle manufacturers. The environmental calculation is more complicated than electric equals clean. Electricity generation produces emissions in most markets. In China, where coal still accounts for a significant share of electricity production, the net emissions benefit of an electric flying vehicle is meaningfully reduced compared to a calculation based purely on the vehicle's own operation. The benefit improves as grid decarbonization progresses, but it does not start from the baseline the promotional framing implies. Battery production for flying vehicles requires lithium, cobalt, nickel, and rare earth elements extracted from the ground through processes that carry their own environmental costs. The mining operations required to supply a globally scaled flying vehicle industry would represent a significant expansion of current extraction with land, water, and community impacts that receive essentially no attention in the transportation revolution narrative. Battery disposal at the end of service life is a problem the electric vehicle industry has not fully solved at current scale. Flying vehicles, with their demanding duty cycles and performance requirements, would likely see faster battery cycling than ground vehicles. A globally scaled flying vehicle fleet would generate a battery waste stream that represents a material management challenge with real long-term environmental implications. None of this is an argument that the technology should not be developed. It is an argument for honest accounting that the promotional version of this story consistently omits. Every government watching this development is simultaneously thinking about civilian applications and military ones. The technology does not distinguish between them. The same capabilities that make autonomous flying vehicles attractive for civilian logistics, rapid movement across terrain that roads cannot cross, operation without a licensed human operator, low acquisition cost relative to conventional aircraft, have direct military applications that defense planners in every major country are actively working through. The Pentagon is funding air mobility programs for ground forces. Autonomous aircraft capable of rapid resupply, medical evacuation, and personnel movement in environments where conventional vehicles cannot operate and helicopter costs are prohibitive. The same vehicle that delivers medicine to a remote mountain village in one scenario delivers ammunition to a forward position in another. The asymmetric threat dimension receives the least public attention and deserves the most serious consideration. A personal flying vehicle platform that is inexpensive, widely available, and capable of carrying a payload through low-altitude airspace that existing air defense systems were not designed to monitor at that flight profile, represents a genuine security challenge. Detection, identification, and response to low, slow, small flying objects at the scale that widespread civilian deployment would create is a problem that defense establishments in every major country are working on but have not fully solved. This is not a reason to halt development. It is a reason for the security and regulatory frameworks to develop at a pace that keeps up with the technology rather than running years behind it as they currently are in most markets. Now, the engine, while one group of engineers was working out how to make the sky accessible, another group was solving a problem that affects every person who has ever stood at a fuel pump watching the numbers climb. In April 2026, Geely walked onto a stage at the Beijing Auto Show and put a number on a screen that silenced automotive engineers on 3 continents: 106 miles per gallon. Not in a laboratory, not under controlled ideal conditions. On a public road in Hainan province in a mid-size family sedan with Guinness World Records, officials present for the entire test, verifying every measurement taken from start to finish. To understand why that number produced the reaction it did, you need to understand what thermal efficiency means in practice. When fuel burns inside a conventional engine, only a fraction of the energy released actually moves the vehicle forward. Everything else becomes heat that exits through the exhaust or dissipates into the engine components. The fraction that becomes forward motion is the thermal efficiency percentage. A regular gasoline engine converts approximately 30 to 35% of its fuel into motion. Toyota spent 30 years developing hybrid technology and achieved 41% in its most advanced production engine. That 41% number was considered, for years, the practical ceiling of what was achievable in a mass-produced vehicle, the benchmark everyone else aimed for and nobody matched. Geely's BHE 15 engine hits 48.41%, certified by Guinness, verified by independent testing, stamped in the record books. The comparison that makes this land with its full weight is Formula One, the most sophisticated internal combustion engines ever built by human beings. Engines that cost millions of dollars each and are rebuilt after every single race by teams of specialized engineers. Those engines operate at approximately 50% thermal efficiency. Geely built an engine for a family sedan priced under $10,000 that sits within 2 percentage points of that benchmark. When paired with a 308 horsepower electric motor and an AI energy management system continuously optimizing between engine power, battery power, and regenerative recovery in real time, the result is 106 miles per gallon on a public road in a car a regular family can afford. Toyota drove a Prius from Los Angeles to New York in 2024 to demonstrate peak hybrid efficiency. That journey averaged 92.9 miles per gallon. The automotive press celebrated it as a landmark. Geely beats it by more than 12% in a cheaper car. And Geely is not alone. BYD achieved 46.06% thermal efficiency in its 5th generation hybrid system. Its top model covers over 1,300 miles on a single tank combined with a full battery charge. Miami to Boston without stopping for fuel. Changan, Ceres, GAC, Chery, and Great Wall have all launched comparable systems within 18 months of each other. A thermal efficiency figure that was cutting-edge laboratory science 2 years ago is now a baseline expectation across the Chinese market. The transmission mechanism into Western markets is already built. Geely owns Volvo, it owns Polestar, it runs a luxury joint venture with Mercedes-Benz. It licenses powertrain technology through its Horse Powertrain Alliance. These engines will appear under European and American hoods whether legacy manufacturers develop their own equivalents or not. The record set in Hainan province is coming to dealerships in every major market. The timeline is years, not decades. Pull back now and look at the complete picture. 109 years of the same promise from the same direction, and the breakthrough came from somewhere nobody was looking closely enough. Not because of superior engineering genius, not because of some innate technological advantage unavailable to anyone else, because someone built the floor, the manufacturing infrastructure, the regulatory frameworks developed alongside the products they governed, the government commitment treating this as a national priority, deserving coordinated investment rather than a market experiment to be left entirely to private capital, navigating existing frameworks designed for previous eras. The vehicles that exist because of that floor are genuinely remarkable. Autonomous certified passenger aircraft operating commercial routes today. A foldable flying vehicle with 5,000 pre-orders and a factory ready to produce 10,000 units per year. A personal flying vehicle priced below $5,000. The largest electric passenger aircraft ever built. And an engine for a family car sitting within 2 percentage points of Formula One thermal efficiency with 106 miles per gallon certified on a public road. The obstacles between here and mass adoption are also real. Regulatory frameworks still being written in most markets. Infrastructure that does not yet exist at necessary scale. Environmental calculations more complicated than the promotional narrative acknowledges. Security implications that defense establishments are still working through. Noise impacts on urban environments that urban planning frameworks have not yet grappled with seriously. Public trust that needs to be built, one flight, one uneventful landing, one ordinary person climbing out and saying that was completely fine at a time. These are not small obstacles. They are the kind of obstacles that take years to work through rather than months. The technology being available does not mean the full transformation happens immediately. Electricity was available before the electrical grid existed. The automobile existed before paved roads did. The speed of adoption is determined not just by what the technology can do, but by what the surrounding systems are ready to support. What is different this time is that the technology is not waiting. It is not sitting in development facilities accumulating test hours. It is in the air, it is in the record books, it is on order lists with real deposits behind the real names of real people who looked at what has been built and decided they wanted to be part of what comes next. The 20th century belonged to the countries that invented the jet engine, built the commercial aviation network, and wrote the rules that govern the global sky. That century of air travel leadership shaped economic geography, tourism, trade, and the fundamental understanding of what was possible in terms of where human beings could go and how fast they could get there. The 21st century sky is being shaped right now, not through the institutional channels that shaped the last century's aviation industry, through a $4,937 personal vehicle that lifts off a driveway, through an autonomous pod that asks nothing of its passenger except to choose a destination, through an engine for a family car that made Guinness World Records officials stand on a public road in Hainan province and certify that what they had just witnessed was real. 109 years of promises. The one that was kept did not come from where anyone expected it. The only question worth asking now is what comes next. And the answer to that question is being written in Chinese cities, on Chinese roads, and in Chinese factories that are already at capacity. The rest of the world has work to do. If this gave you the complete story rather than just the headline, hit the like button before you go. It makes a genuine difference to whether this reaches people who want substance. Subscribe and turn on notifications because the next chapter of this story is already moving and you want to be there when it breaks. Drop a comment and tell me which part of this surprised you most. The $4,937 price, the 106 miles per gallon, or the fact that ordinary people are already flying in autonomous pods over Chinese cities while we are still debating whether it is theoretically possible. I read everything. See you in the next one.